next up, let's talk about complementary events. Now, for complementary events, these events are exact opposites of each other. And we're very frequently going to see the word not when we're describing complementary events. So complementary events would be playing soccer and not playing soccer, or getting a raise and not getting a raise. So this word not, as I said, is a very good indication of complementary events, but it doesn't necessarily have to be. So for example, winning the lotto or losing the lotto, you can either only do one or the other, and so those are also complementary events. All right, so if we look at playing soccer and not playing soccer, and we call playing soccer event A, then not playing soccer is what we call A's complement. And these two events together are going to cover all the possible outcomes, right? So there isn't something in between where you somehow don't play soccer, but you also do not play soccer. You're part of either one or the other. No in-betweens, right? So there isn't a third option. And so the probability of A plus the probability of A's complement is equal to 1. And that basically just says if you select somebody at random, they either play soccer or they don't. Okay, so because we've got this quality here, probability of A plus the probability of A's complement, also often just called not A, is equal to 1, we get that the probability of A is equal to 1 minus the probability of A's complement, or the probabilities of A's complement is equal to 1 minus the probability of A. And these are equations that we often use, especially when it's far more easy to find the complement of an event than it is to find the probability of an event itself. Okay, so let's quickly look at some Venn diagrams, right, and see how this would work in that context. So let A be playing soccer, B be playing hockey, and C be playing golf, and this is represented on this Venn diagram here with a sample size of 80. So what is the probability that a randomly selected player does not play soccer? Okay, so here we've got that word not, and so we can use the complement. So A is the probability of playing soccer, and then A's complement is absolutely everything that is not A. So everything that falls outside of A is going to be counted. So to find the probability of A's complement, we can just take 1 minus the probability of A, and there are 37 people who play soccer out of the 80, so that will be 1 minus the 37 over 80, and that will be the 43 over 80. Okay, cool. So if we then continue from there, it is now your turn to pause the video and quickly try this example. Fantastic. I hope that you're shaking loose some cobwebs. Let's see what we can do here. So we've got this test for PEDs. It's 95% accurate if you're actually a drug user, and 99% accurate if the subject does not use PEDs. So we've got 500 athletes, 20 use it, the rest do not, right? How many positive tests do we expect? Now here we've got the sort of information that we love to put into a tree diagram, because we have the first event, do they or do they not use performance enhancing drugs, and then the second event, which is when we test them, do they test positive or not? Right, so event 1 on my tree diagram, right, I'm just going to say is drugs, right, and then no drugs. Okay, that's pretty simple and descriptive. So we know that 20 out of the 500 actually use performance enhancing drugs. So that is going to be the probability there. And that must mean that everybody else does not. So that's going to be 480 over 500. Okay, right. So then we test them. Now they use this word accuracy. So accuracy means that the result of the test is going to reflect the reality. Okay, so if somebody does use drugs, accurate means that the test says they do use drugs, and that we call a positive, right? So the probability of getting a positive if you use drugs is the 0.99. And the probability of getting a negative if you use the drugs is going to be the 0.01, because you've either got to be positive or negative, right? Then it says that I got this wrong. It should be 0.95 for the positive, and here 0.05, because we're talking about the accuracy rate for the subject who does actually use the performance enhancing drugs. And then here we'll then have the positive and the negative. And now here we've just got to be careful. Testing negative when you don't use drugs, that is accurate. So in order to have our 99% accuracy, you need a 0.99% chance of testing negative if you are in fact not using drugs, and then this will be the 0.01. Okay, so what did we need to find out is how many positive tests we expect. Now, when it comes to a tree diagram, we want to find all of the possible paths, the possible branches that actually satisfy what we're trying to find, right? So we're trying to find the positive tests, and positive tests can be obtained by having somebody who does drugs and then tests positive, and having somebody who does not do drugs but then tests positive. So those are our two potential ways in which a positive test can happen. And the rule for a tree diagram is that we multiply as we go along the tree diagram, and then we add up whatever we get in those columns. So here, to find the probability of doing drugs and testing positive, we've got to go and take the 20 over 500 and multiply that by the 0.95. And when you do that, we get an answer out of 19 over 500, right? Which I'll write as 0.038, okay? And then the probability of not doing drugs and still testing positive will be 480 over 500 times the 0.01. And so we get a very, very small answer of 0.0096, which is actually kind of nice, because you do want it to be very unlikely that somebody who does drugs won't test positive. Otherwise, you'll possibly ruin a lot of careers or lives. Okay, so 0.038 plus the 0.0096 is going to be our probability of getting a positive test. Okay, so that's going to be 0.0476, and that's the probability of a positive test, right? But now we want to know how many of these positive tests do we expect, right? So the probability of the positives is going to be the number of positives over the sample size, right? So the probability of the positive was 0.0476. That's going to be the number of positives divided by the sample size, which is 500. And so we just need to take this 0.046, multiply that by 500, and then we get that the number of positive tests that we expect is going to be 23,8. Now, in reality, we know that we can't get a fraction of a positive test, but often when we apply probabilities in order to see how many we're going to expect, because it's theoretical and mathematical, we will sometimes get fractions. Okay, so now you can pause the video again and try this following question. Okay, right, so we've got a researcher, and this person wants to decide whether gender is independent of smoking. Now, the researcher collects data from 300 people, of which 125 are male and 175 are female. Of the 300 people, only 80 smoke, and 30 of those who smoke are males. So the first question there was to construct a contingency table, right? So for the contingency table, we know it's a two-way table in which we're going to classify these two events, the one being gender and the other one being smoking or not, right? So I'm going to make my columns male and female. and I'm going to make my rows either smoking or not smoking. And because I want to be creative, I'm just going to draw a line like that. That means not smoking. Okay. And then we know that we've got to have totals, right? So I'm going to draw my column like this. And like this. Okay. And then we know, okay, we have 300 people. Fantastic. Then we know that 175 of those are female. So here in the total row, I'm going to have the 175 for female, and for the male, I'm going to have 125. Then we know that only 80 of these people smoke, so there's the 80 there, and 30 of those who smoke are males. So that's what we get if we put in the information that we've been given, but we are now in the wonderful position where we can find the rest of the values because of what we have been given. So in this total column, we know that 80 plus some number has to be 300. So 300 minus the 80 is 220. So there's 220 people who don't smoke. Then we know that if 30 of the smokers are male, the other 50 have to be female. And then we know that if 50 of the females smoke, then 125 of them do not, and if 30 of the males smoke, then 95 of them do not. And now we've got a complete contingency table, and now we've got to determine whether gender is independent of smoking. Now we need to remember how to show that something is independent. And the way to show that something is independent is to show that the probability of those two things happening together, the probability of A and B, is equal to the probability of A multiplied by the probability of B. Right, okay, so let's find the probability of being a male and smoking. Now, the probability of being a male and smoking, the number of ways that can happen is only 30, right? So here, the probability of, and I'm just going to use A and B, where A is male, B is smoking, is going to be 30 out of our 300 people. Then, the probability of A must then be the probability of being a male. So out of the 300, how many are male? Well, that's going to be 125. So that's going to be 125 over 300. And then the probability of smoking is going to be the 80 people who smoke divided by the 300 people in total. So this is going to be 80 over 300. Okay, so then the probability of A multiplied by the probability of B is equal to 125 over 300 times 80 over 300. Okay, and we then get 125 times 80 over 300 times 300, right? And that gives us 1 over 9, which is 0,111111. Okay, so I'm just going to write 0,11. But then 30 divided by 300 is 1 over 10, which is then 0,1. So we see that the probability of A and B is not equal to the probability of A times B, and this means that these events are not independent. So there is some sort of relationship between your gender and your likelihood to smoke or not to smoke.